Hello, in this video we're going to talk about AP Chemistry's topic 5.3, the concentration changes over time. This is going to focus on the integrated rate laws and how we can use the integrated rate laws to determine the order of reaction and also how we can use it to determine the value of a rate constant as well as the concentration of a reactant as time progresses. So we are going to focus in on a very simple reaction, substance A decomposing into products. The way that we can represent the rate of this reaction, or what rate means in this reaction, is how does the concentration of A change as time progresses? We know that A is going to disappear as the reaction takes place, but the rate is how does it disappear? And the rate can be in three different orders that we've talked about. The rate can either be zero order, where the rate is not going to change as the concentration of A changes. In other words, as A disappears, the rate will not change. It'll stay constant. Or if it's with first order, then the rate will change as the concentration of A disappears. So we write the rate equation. Rate equals K times the concentration of A to the first power. And that means as the concentration of A goes down, the rate will also go down linearly. If we look at if the reaction is second order with respect to A, that means that the rate equals a rate constant times A to the concentration of A to the second power, which means as A disappears, it'll be a quadratic function. The rate will disappear quadratically. So as you lose A, you're going to quadratically decrease the rate of the reaction. So let's go ahead and write the rate in this form equal to the rate in this form for each order. So for a zero order reaction, the change in concentration of A over the change in concentration of T, and I'm going to write this in terms of a differential because we're going to do some integration here. If you've taken calculus, you know what this means. If you haven't, think of it in terms of the change of A over change in time. So the negative D concentration of A over dt, so the rate of the decrease of concentration of A for a zero order reaction is just equal to the rate constant. Now I am going to integrate this equation, but if you don't know what integrate means, then you're just going to see our final integrated rate law. If you do know what integration means, then you'll be able to figure out how to do this integration. But I'm going to integrate both sides with respect to time. And if you do that, you will end up with an equation that looks like this. The concentration of A at time t minus the initial concentration of A is equal to the rate constant times T. So if this reaction is a zero order reaction, then this equation is true. Now, we don't know if this is a zero order reaction or not, but if this is a zero order reaction, in other words, the rate is zero order with respect to A, then this equation will be the equation we can use for this reaction. If it's a first order reaction, then the rate is not going to equal K, it's going to equal K times the concentration of A. So if we integrate this equation, you will end up with an equation that looks like this. The natural log of the concentration of A at time t minus the natural log of the concentration of A at time 0 equals K times T negative. Oh, and I forgot the negative sign on this side. Sorry about that. Negative to the other side. So negative KT, negative KT. Okay, so if this reaction is first order, the rate is first order with respect to substance A, then this integrated rate law holds true. If we know the initial concentration of A and the value of the rate constant, we can calculate how much A will be left at some amount of time later on. So this is our integrated rate law for a first order reaction. If it's a second order reaction, then negative dA over dt is going to equal the rate constant times the concentration of A to the second power. And so if we integrate this equation, you will end up with 1 over the concentration of A at time t minus 1 over the concentration of A at time 0 equals KT. So these are our three integrated rate laws, and each one is specific to the order of the reaction. And so you have to know what the order of reaction is to know which equation you can use. So how can we figure out the order of reaction? Well, the answer, and by the way, all three of these equations are on your equation sheet. Actually, I don't think the zero order one is, but the other two are. So these are the three integrated rate law equations that allow us to calculate the concentration of A at some time in the reaction. So how can we figure out the order of reaction so we know which one to use? Well, to do that, we're going to rearrange these into a way that will make them a little more useful. So let me show you what we're going to do. We are going to linearize each of these equations. In other words, if you think about the equation of a line, y equals mx plus b, I can rearrange these equations and do some graphical analysis that will help us figure out which equation to use. So I'm going to rearrange this equation. And if you look at this equation has a very similar form to the general linear equation of a line, where AT would be our y variable, negative k would be our slope, t would be our x variable, and the initial concentration of A would be the y-intercept. What this means is if we graph the concentration of A versus time, if it gives us a linear graph, then we know that we have a zero order equation. So if we have data that we've analyzed, in other words, we've monitored a reaction and we've measured the concentration of A as time goes along, and we graph the concentration of A as time goes along, and it gives us a line, then we know it's a zero order reaction. If it's first order, we'll get a curve when we do this graph. If it's second order, we'll get a curve when we do this graph. If it's a line, then we know it's a zero order reaction. So what if it is a curve? Then we know it's not zero order, so we have to do something else. So I'm going to rearrange our first order integrated rate law and make it look like the equation of a line. So look at this. Y variable would be natural log of A. Slope would be negative k. T is our x variable, and B is the natural log of the initial concentration of A. So now if we do a graph, and instead of graphing concentration versus time, we graph the natural log of the concentration versus time. If this gives us a linear graph, then we know we have a first order reaction. So graphing natural log of A versus time, if it gives us a line, we know we have a first order reaction. If it gives us a curve of any sort, then we know that it's not first order when we graph natural log of A versus time. Then we know that it's either zero order or it's second order. So what about second order reactions? Well, again, let's rearrange the equation. 1 over the concentration of A at time t equals kT plus the inverse of concentration of A initial. So y equals mx plus b. Y would be our inverse of concentration of A, slope is the value of k, and b is the inverse of our concentration initial of substance A. So if we graph the inverse of concentration of A versus time, and this gives us a straight line with positive slope, then we know that we have a second order reaction. So graphing the inverse of concentration versus time, if it gives us a straight line, we know we have a second order reaction. If it gives us a curve of any sort, then we know it's either first order or zero order. So doing graphical analysis of our data allows us to figure out if it's zero order, first order, second order. A line graphing concentration versus time means it's zero order. A line graph of natural log of concentration of A versus T means that it's first order. And a line graph, if we graph the inverse of concentration of A versus time, means that it is second order. So that's a useful way to use graphical analysis to figure out what order a reaction is. So we're going to do a practice problem and just see how this works. So here is an example that I have already written up with some questions. So a reaction of substance A decomposing to substance B and C was analyzed, and after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and 6 seconds, these were the concentrations of substance A as time went along. So this is our data as the reaction took place. We took this data and graphed it. We graphed just the concentration of substance A versus time, and here is the graph of that data, concentration of A versus time, and it gives us a curve. We then took the natural log of all these concentrations and graphed that versus time, and we got this graph. Then we took the inverse of all these concentrations and graphed the inverse versus time, and this was the graph that we got. And if you'll notice, we have a line. So what does that mean for this reaction? Well, if we graph the inverse of concentration versus time and it gives us a line, then we know that it is a second order reaction. So what is the order of the reaction? The graph that gave us the line was the second order graph. So we know it's second order. So now we can ignore all of this information and just focus on the second order graph, and we know that this is a second order reaction. What that means is our rate equation for this reaction is going to equal the rate constant times the concentration of A to the second power, because we now know it's second order. So this is going to be our rate equation for this. So the next question, what is the initial concentration of A? Notice that we do not have the initial concentration in our data. We don't know how much there was initially. But we can solve for this graphically, because if we look at the equation here, we know that this is a line, concentration of A over T, and we can extend it back to time 0 and figure out the concentration. So just looking at the graph, extending our graph back to time 0, we get 10. Now, we got to be careful with this, because that 10 means the inverse of the concentration. So the inverse of the concentration of A at time 0 is equal to 10 inverse molar. That's not the initial concentration. That's the inverse of the concentration. So if we rearrange this equation and solve for the concentration of A at time 0, the inverse of 10 is 0.10 molar. So that's our initial concentration of substance A. Again, we can't just take it straight off the graph, because that's the inverse of the concentration. But we can solve for the initial concentration by taking the inverse of that y-intercept. So next, we want to solve for the value of K. Now remember, from our integrated rate equation, the inverse of the concentration of A at time t is equal to the negative K times T plus the inverse of the concentration of A initial. K is the slope of our line. Remember, K is equal to slope for the graph of inverse of A versus T. So if we can calculate the slope of this line right here, then we know the value of K. And I'm sorry, this shouldn't have been a negative, that should have been a positive. Okay, so all we have to do is calculate the slope of the line. So the slope of the line is equal to our change in y over change in x. We just have to pick 2 points on the line. I'm going to pick this point right here as one of our points, and this point right here as one of our points. Point 1, point 2. So y2, our y value at point 2, is equal to 50 inverse molar, and our y value at point 1 is 20 inverse molar. And if we find the change in x, our second point, x value, is 4 seconds. And our first x value is 1, so 1 second. That gives us 30 molar inverse over 3 seconds. So the value of our slope and the value of our K is 10 inverse molar inverse seconds, because the slope of our inverse concentration graph is the value of K. So now we know the value of K. Our last problem is asking what's the concentration of A at a specific time, 15 seconds. We can't do this one graphically because our graph does not go far enough. It only goes to 6 seconds. So now we're going to use our integrated rate equation to solve for the concentration of A at time t. So our integrated rate equation is this, and we're simply going to plug in everything we know at this point. We know the value of K. We know the initial concentration of A because we solved for it in part B. We know T because we're solving for 15 seconds. So that will allow us to solve for the concentration of A at time t. So let's go ahead and plug in everything we know. The value of K is 10 inverse molar inverse seconds. The time that we're solving for is 15 seconds. And our initial concentration of A was 0.10 molar. So now all we have to do is do the algebra to solve for the concentration of A. I am not going to go through all that algebra, but you can do it on your own just to make sure you know what you're doing. And if you solve for the concentration of A, you will get 0.0071 molar. And that is the initial concentration of A. I mean, sorry, not initial concentration. That's the concentration of A at time t. So that's where I'm going to stop for now. If you have any questions, please let me know. But the important thing to remember here is that graphs allow you to figure out, graphs of the integrated rate laws allow you to figure out whether you have zero order, first order, second order, and the integrated rate laws allow you to calculate the concentration of your reactant at any time. If you have any questions, please let me know. I know that I was very jumbly on this, but hopefully it was helpful. Good luck.